What's going on, guys? In this video, we're going to be doing part 1 of our Calculus 1 final review. In this video, we'll be covering limits, and then we're going to be talking about derivatives, kind of like, all the different rules with derivatives. We'll be talking about some things that we can do with derivatives, and in the next video, in the part 2 video, that'll be the last video, I'll only make this a two-parter, we're going to be doing the applications of derivatives, right? So we're going to be doing things like optimization, finding mins and maxes, different things like that, right? And we'll also be talking about integrals, all right? So let's get into more of what we're going to be doing in this video. So you can see I have all the timestamps for what we're going to be doing, and we'll start off with evaluating non-infinite limits. We'll continue on to talk about continuity and evaluating infinite limits. We'll talk about the limit definition of a derivative, everybody's favorite. Honestly, that was my least favorite part of calculus, but we're going to do it. We're going to be doing some derivative problems, like just kind of working with some derivative rules, and we're going to be doing implicit differentiation. We'll be doing exponential growth and decay, related rates, and linear approximations and differentials. Okay, and I have all the timestamps listed, so if if you're struggling on one specific part, like related rates, I know related rates and optimization are like the top two things that really trip everybody up, right? If you're struggling on related rates and you're not really struggling on much of this other stuff, maybe go to that part first, and that's what you can use a timestamp for. All right, so let's get into our first problem. All right, and we're starting off with evaluating non-infinite limits. Okay, our first problem says for the piecewise function f of x equals, and it equals the absolute value of 2x plus 3 when x is less than or equal to 2, and it equals to 3 times the quantity x plus 1 squared if x is greater than 2. And we want to find the limits when we want to find the limit when x is approaching 2 from the negative side of f of x, the limit as x approaches 2 from the positive side of f of x, and the limit as x approaches 2 of f of x. All right, so we're going to be doing two one-sided limits, and then we're going to be doing just a double-sided limit, seeing if that exists, right? So we don't need to graph this, okay? That's the biggest thing. You might be wondering, okay, how do I graph 3 times the quantity x plus 1 squared, right? And that might be a little confusing to you, and that's no big deal, right? We don't need to actually graph this, okay? What we do need to point out, right, for our first limit, we can do the limit as x approaches 2 from the negative side of f of x. We need to figure out what function we're actually going to be doing, because we have a piecewise function. There's two functions, and it's only when x is either less than or greater than, right? So we're dealing right now from the left-hand side, right? That means that we're going to be dealing with x being less than 2 leading up to 2, right? If that kind of makes sense, right? We're going to be starting from that left-hand side of the graph. So we're going to be taking that function, the absolute value of 2x plus 3. Okay, so we're going to now substitute in our function. All right, and now all we really have to do is just plug in 2, right? So we write 2, and we can plug it in here. 2 times 2 plus 3, right? And that's just going to be equal to 2 times 2 is 4 plus 3 is 7. Okay, so we found our first limit. Let's move on to the next one. We're going to talk about the limit as x approaches 2 from the positive side of f of x. All right, now as x approaches 2 from the positive side, we're dealing with the other function now. The 3 times x plus 1 squared. Right, so we can plug in again, and honestly we don't even need to put the limit again. We can just do 3 times 2 plus 1 squared. So we're going to get 27. Okay, because 3 times, that'll be a 9, so it's 27. All right, so now comes the big question of what about the limit as x approaches 2 of f of x? Okay, remember, what happens with one-sided limits, right? The reason why we take one-sided limits, maybe these two limits aren't going to match, right? In which case the limit from both sides, if the limit from the left side isn't equal to the limit from the right side, so they look something like this, right? They're approaching 2 and it looks like this. Well, that means that the limit as x approaches 2 doesn't exist, okay? It doesn't exist. So we can just write dne, right? The reason why we know that they don't match up is because 7 is not the same thing as 27, okay? So that will conclude our first problem. Okay, starting you guys off with something that's not the worst thing in the world here, okay? So moving on to something that is not that fun. I want you to demonstrate the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. Okay? Now, you may be thinking, all right, well, I'm going to use the limit laws, split this up, and say that, okay, well, this is the same thing as the limit as x approaches 0 of x squared times the limit of x approaches 0 of sine of 1 over x. Now, a big mistake that I assume a lot of people would end up making in this problem is they would do this, right? And they would say, oh, well, this limit right here is just 0, so the answer is 0. But here's the problem with that. While this limit is 0, this limit doesn't exist. Okay? The reason why this doesn't exist, and if you haven't dealt with a sine of 1 over x graph in your calculus class, you probably won't have to worry about something like this on your final, but you know, maybe you did something like this earlier in the year and you don't remember, in which case, you know, that's always a possibility, right? So the problem with sine of 1 over x is that as you get closer and closer to 0, this thing starts oscillating an infinite number of times, right? And so it's going to look like that, right? And it's oscillating from 1 to -1. I knew I drew that kind of sloppily. Okay, so the problem that you're going to have to deal with is, okay, well, is the limit 1? Is it -1? Is it 0? You know, you don't know. So the limit ends up not existing. Okay, so that's the problem with sine of 1 over x. Okay, and if you don't know that graph, you know, or maybe you like I don't know what the conditions are going to be for your final. You know, you would know better than me. Do you have a calculator? Do you not? I personally I took AP calculus, so I ended up having a calculator for some parts and not for others. So you know, this would most likely be a graphing part, so you actually are able to see what sine of 1 over x looks like, because I don't think that, you know, many of you would be able to actually graph that. Like, I don't think I would. So I'm just giving you some context for when you would see this problem if you're like, oh my god, how would I ever know this? Okay, so what we're gonna have to do here is use something called squeeze theorem. Okay, that's the other way we can evaluate limits. Now the squeeze theorem says that if you have this function's, we'll call this function g of x, right? We'll say that g of x equals x squared sine of 1 over x. Okay? Now, for squeeze theorem, we want to find two functions that are greater than and less than, and we'll have or equal to as well, of our function at any given x, right? So we have f of x and we have h of x. So the big thing with these limits of these functions is that, well, we want the limit as x approaches 0 of f of x to equal the limit as x approaches 0 of h of x. Okay, and we want these limits in this case to equal 0. The reason why I'm saying equals 0 is because we're given that in the problem. We're trying to find that it's equal to 0. Okay, so if these limits are equal to 0, and this is true, right, that g of x is always going to be in between f of x and h of x, or it could be equal to both of them, right, or one of them, then we know that the limit as x approaches 0 of g of x will equal 0. Okay, now you can't just call that and be like, okay, that's my answer, I just use squeeze theorem. That's not how squeeze theorem works. Okay, you actually have to find functions that'll do that. Okay, but we can do that. Let's find a function first. This will probably be the easier one, that's always greater than g of x, but the limit as x approaches 0 of that function equals 0. Okay, now think about it. If our g of x is x squared times sine of 1 over x, x squared, okay, you have the x squared, and that's, you know, just dependent on x squared, whatever, but sine of 1 over x, that's always going to be between -1 and 1. Okay, so that kind of tells you right away that if you, I mean, your maximum value could just be x squared, right? And your minimum function could be negative x squared, okay? Because the smallest this thing could ever be is when sine of 1 over x is negative 1, and that would make this thing negative x squared. The biggest it could ever be is when it's 1, and that would give you x squared. So right there is your two functions. All right? So kind of interesting stuff with squeeze theorem. Now, we know that the limit, okay, the limit as x approaches 0 of negative x squared is equal to the limit as x approaches 0 of x squared, and these are both equal to 0, right? So that means that the limit as x approaches 0 of x squared sine of 1 over x is equal to 0. All right? So really, really, really interesting stuff there. And you can say, by the way, you might want to state that you did this by squeeze theorem. Okay, so squeeze theorem, I think, is a topic that gets glossed over and might appear on your final as one of the tougher questions. That's why I really wanted to make sure that I actually covered it. And by the way, let me show you a graphical representation of how squeeze theorem works, because, you know, just showing you this, maybe some of you are still confused on how we're able to actually say that this thing is 0. Okay, let me say that I'm going to draw f of x in, well, actually, let me draw my axes first. Okay, we'll draw this over here. Okay, we'll say that f of x is going to be in red, g of x is going to be in green, and then we're going to do h of x in blue. Okay, let's say f of x, okay, we'll say f of x is some graph right here. Okay, I'm not drawing the x squared graphs or anything like that right now. Let's say the h of x graph is something like this. Okay, so you have h of x and we have f of x. Now what we're saying here, okay, and we're trying to find the limit of g of x as x approaches 0. Well, let's say we have g of x coming in, and it's always less than or equal to h of x, and it's always greater than or equal to f of x. Well, you have this g of x coming in, okay, and it gets pinched in between f of x and h of x. As you can see, it gets pinched here and it gets pinched here. So it's bounded by these two curves, and if they both equal 0, this one has to also equal 0. So they all converge at 0. But like I said, g of x can't escape that the clutches of f of x and h of x, right? It can't go up here, right? It can't do anything like that. It could do something like this, where it goes to the top, touches h of x or something like that, right? But it can never go outside there. It's always going to converge to 0, right? So that's the idea with squeeze theorem, okay? So now we're going to move on to continuity. Okay, problem 3. Is the following function continuous at x equals 0? If it's discontinuous, what kind of discontinuity is it? And our function here is f of x equals, it's going to equal cosine x when x is less than 0, 0 if x is equal to 0, and 1 minus x squared if x is greater than 0. Okay, so we're trying to see if this thing is continuous at x equals 0. Okay, so we should first off find out what happens when the limit as x approaches 0 from the negative side of f of x equals the limit as x approaches 0 from the positive side of f of x equals f of 0. Okay, so if both one-sided limits agree with the actual value at that x equals 0 mark, all right, well, then we know that that thing is continuous, right? So because, and we're saying, usually it's continuous if the left-sided limit equals the right-sided limit, but now we also have a different value completely at x equals 0, right? We're defining it to be 0, okay? So we also have to make sure that that agrees, okay, or else it's not continuous, it's going to be some kind of discontinuity, which we would have to define. All right, so we got to find all of these things, right, except for f of 0, because we know that that's equal to 0, right? So we can actually even say equal to 0. So first off, the limit as x approaches 0 from the negative side of f of x. Okay, that's equal to the limit as x approaches 0 from the negative side of, well, what's our function coming from the negative side? It's cosine x, right? Because that's when x is less than 0. So we have cosine x here. Now this is not the same thing as the sine of 1 over x, okay? The sine of 1 over x, that's a completely different graph. You know the graph of cosine x, and you know what it approaches as x equals 0 from the negative side, right? It will and it approaches the same thing as if it approached it from the positive side, or if it just approached it from both sides, right? It's approaching 1, right? Cosine of 0 is 1. So that already doesn't agree. So we know we have some kind of discontinuity going on here, because 1 is not equal to 0. So let's figure out, let's try to diagnose what kind of discontinuity we have here. Okay, by taking the limit as x approaches 0 from the positive side of f of x. In doing this, we need to figure out what function we're going to use, and here it's going to be that 1 minus x squared, because that's when x is greater than 0. Okay, that's our function on the positive side of 0. Okay, and we can see here that that would equal 1 minus 0 squared, which is just 1. Okay, so we have 1. We have 1's coming from the left and the right hand sides, okay? But that doesn't agree with the value that's actually there. So we do have a discontinuity. What kind of discontinuity would we have? If you think about it, our graphs look something like this, right? I'm not going to draw exactly what they look like, right? But we have something coming up here, right? And it's an open circle. And we have something coming this way, right? And it's an open circle, okay? The actual value is right here. So what kind of discontinuity is this? Well, we have a couple different things to choose from. You know, most of you already can guess it. There's infinite, there's jump, there's removable, right? So there's I believe 3 main kinds of discontinuities. There may be one more that I'm forgetting, but I believe it's just these 3. And, well, you can see here that this is a removable discontinuity, right? We're just removing a single point from this function, or else it would have been continuous. So we can say that this is a removable discontinuity. All right, and there you go. There's problem 3. Now for problem 4, it wants us to create a piecewise function defining f of 2 so that f is going to be continuous at 2, right? And right now f of x is equal to x squared minus x minus 2 all over x minus 2. Okay, so we want to make f continuous at 2. Why is it not continuous at 2? Well, let's take a look. We know that if we plug in f of 2 right here, our denominator, okay, so we'll have some gibberish in the numerator, I don't know yet, but we'll have a 2 minus 2 in the denominator. That gives us a 0 something over 0, right? And in this case it'll be 0 over 0, so it makes it even like worse, but you still have something over 0, so that's going to create a discontinuity. Okay, so what we're gonna do here is we'll figure out what is the limit as x approaches 2 from the negative side of this function, and what is it from the right hand side. Okay, and well, then we would have to figure out what could we put in, right? So what could we put into our piecewise function? Like, I guess this value would become our f of 2, right? Not in this case, right, we would define a new function. So I mean, it's kind of, I'm cross-naming things in a way, because I'm going to define a new piecewise function where it's like this, and it'll still be called f of x, but hopefully you guys get the point, right? So we want this to be equal to f of 2. So we got to modify this function a little bit. All right, so what we're going to do is just plug in here, right? We have our function x squared minus x minus 2 over x minus 2. Okay? And, well, how are we going to actually evaluate this limit, right? This limit, we plug in 2, we get a 0 in the denominator. Well, you can see that we have that nice quadratic on top. So we can just factor that, right? Get the limit as x approaches 2 from the negative side of, well, let's see how we factor this, right? I like to do this little x chart. We have -1 and -2. What two numbers add to be -1 and multiply to be -2? Well, that would be, let's see here, it'll be a -2 and a +1. So we can write x minus 2 and x plus 1, right? And we have an x minus 2 in the denominator. So we have those x minus 2's that actually end up canceling out. Just crossing this off for a second. And we just end up with x plus 1, in which case we now can plug in that 2, and, well, we'll just get 2 plus 1 equals 3. Now the thing is, you know, we didn't really have to incorporate anything about this being different from the negative side as the positive side, so if we did this all again with 2 from the positive side, nothing's going to change. We're still going to have the just x plus 1, right? And we'll still have 2 plus 1 equals 3. Okay? So all we have to do here is take that function from before, the one we were just taking the limit of, and we're going to have that be when x is not equal to 3. And then, or sorry, when x is not equal to 2. And then when x is equal to 2, okay, we just say that it's 3. Okay? Because essentially right here we saw that we have another removable discontinuity, just as we had in the last problem, right? The limit from in the last problem, the limit from the left-hand side equaled the limit from the right-hand side, right? They were both 1. But in this case, I mean, the function at that point, right, was 0. Okay? So it wasn't equal to that. So what we're going to do now is just define f of x. So we have f of x now equals x squared minus x minus 2 over x minus 2 if x is not equal to 2, and 3 if x equals 2. All right, perfect. Moving on to infinite limits, and question number 5. Find the limit as x approaches infinity of x squared all over the square root of x to the 4th plus 1 without using L'Hopital's rule. Do the same for the limit as x approaches infinity of 4x cubed plus 6x squared minus 2 all over x cubed minus 5x plus 5. Now a big thing here, I didn't want you to use L'Hopital's rule because I really want you to explain to me why you think why these limits are what they are, right? I want you to develop the intuition of limits at infinity and, you know, what that means when you talk about polynomials and different things like that, okay? So let's just start talking about this first limit here. The limit as x approaches infinity of x squared over square root of x to the 4th plus 1. I want you to think about what the end behavior is going to be. Okay, and what I want you to really see is that, you know, this x to the 4th right here, you know, you take a square root of this and by itself it just becomes x squared. Okay, so this essentially is, you know, an x squared, this denominator, this whole thing is x squared plus a small quantity. It's going to be very small. Now here's the thing, as x approaches infinity, okay, as x approaches infinity, this contribution of this 1 is going to get smaller and smaller and smaller, right? As we're talking about bigger and bigger and bigger numbers, that contribution of 1 is going to be smaller and smaller, right? We don't care about that 1 as much, right? So this thing ends up looking like x squared over x squared, right? It ends up having the same exact end behavior in the fact that it approaches 1, right? So that's what I'm trying to get you to understand with this, and I'll explain it again if this didn't make sense. But, like, you know, hopefully if you have the intuition behind this stuff and you understand this, then you look at a limit like that and you're asked to just evaluate it, you can show it with L'Hopital's rule, then you understand and you're able to check your answer and figure out, okay, that makes sense, right? What I'm trying to get you to see here is that this denominator is going to basically become identical to x squared as it gets to higher and higher and higher x's, okay, because that 1 matters less and less and less. That's why this is happening, okay? So that's the answer to our first limit. Now, for our second limit, we have the limit as x approaches infinity of 4x to the third plus 6x squared minus 2, and that's going to be over x cubed minus 5x plus 5. Another thing that I want to get you to see here, okay, if you've copied this down, you're looking at it, okay, you see a bunch of just garbage kind of after that, the x cubed terms, right? All that garbage doesn't matter, okay, because as x approaches infinity, the x or the term that has x being cubed, right, that's going to get larger and larger and larger, and that's going to kind of alienate the rest of all that stuff, right? That plus 6x squared, right? This will matter less and less and less as x approaches infinity. This minus 5x will matter less and less and less as x approaches infinity, right? And so will the minus 2 and the plus 5. So really, what you end up kind of examining here is 4x cubed over x cubed, which is equal to 4, right? Because the x cubes cancel off, okay? So I really want you to understand this. Now, this probably wouldn't be something that you were actually asked on your final, but it's going to be something that really, really helps you understand limits on your final, okay? That's really why I wanted to include this problem, okay? So hopefully that makes sense. Moving on to number 6, which is to find the horizontal and vertical asymptotes of the function f of x equals 2x squared plus x minus 1 all over x squared plus x minus 2. Now this is definitely something that you're going to see on your final. I'm almost 100% sure of it, finding horizontal and vertical asymptotes. This is huge for limits. Is a very common question to see. Okay, so first let's talk about finding the horizontal asymptotes, because now we're on the topic of infinite limits, we might as well finish it off, right? For horizontal, you're talking about the limit as x approaches infinity and the limit as x approaches negative infinity, right? So for horizontal asymptotes, we're going to start off with the limit as x approaches infinity of this function, right? Which is just x squared plus x minus 1. There we go. Great. Now remember what I said before, that all the terms after the x squared terms in the numerator are going to matter less and less and less as x approaches infinity. So really, this ends up just becoming 2x squared over x squared, and though that'll equal 2. Okay? So we definitely know that we'll end up with a horizontal asymptote at y equals 2. Okay, so that's one of our answers. Now let's talk about the limit as x approaches negative infinity of 2x squared plus x minus 1 over x squared plus x minus 1. You'll see that, of course, you'll also get the same exact idea, right, where you'll have the 2x squared over x squared. But since these, well, first off, these x's are going to be canceling out, right? And so you don't really need to care about it anyway. Also, the x's are being squared, so even if you had like a 2x squared in the numerator, this thing would be approaching positive infinity, because that quantity of x, that large quantity of x, will end up getting squared. It'll become positive, but in which case you wouldn't even have a horizontal asymptote anyway, because it would just be it would end up being like not just settling to anything. Okay, so we still get 2 here, so we can still go with the y equals 2 as our horizontal asymptote. Now we'll talk about vertical asymptotes, which are generally a longer process to figure out. Okay, we have to look at, the only time we're really going to get vertical asymptotes, right, the most common time, is when we have that denominator equaling 0, right? I'm not sure if there are any other times. I honestly can't remember off the top of my head, so correct me if I'm wrong on that. But we have this x squared plus x minus 2, right? And by the way, when I say that, the only times that you're going to have to deal with vertical asymptotes should be only when the denominator is 0. That's the only time that I've ever learned and had to apply on a test, and so I assume that's the exact same for you. So after rambling about that, we need to find out when this denominator is 0. So essentially, we're just going to be finding the zeros of this denominator. Okay? Now, we can see here, since we've done a trinomial like this before, that this is just going to be x minus 1 and x plus 2. Okay? So now what we have to do is we have to, since we know that x equals 1 and x equals negative 2, we have to check that these things are vertical asymptotes. It could just be like the problem we had, it was a couple problems before where we saw that we had something like this, right? But it was a removable discontinuity, right? It wasn't infinite, it was removable. So we have to check that these things are infinite. How do we do that though? We take the limit as x approaches 1 from the negative side. We take it as x approaches 1 from the positive side, and we see if these things are both infinite. It doesn't have to be the same. It doesn't have to be both infinity or both negative infinity. It could be alternating. It doesn't matter. Okay, so let's actually get in and start looking at this. And we won't look at just the denominator, so I don't know why I'm writing that. Oops. All right, here we go. There we go. Over 2x squared plus x minus 1. There we go. So now what we have to do is we have to factor the top and bottom, okay? Because if we don't, then we're going to end up with a 0 in the denominator, right? We've done something like this before, okay? So what we're going to do is just write x minus 1, x plus 2 in the denominator, and we have to factor the numerator, okay? How do we do that? Well, let's create a little side path right here. Okay, that's not how I want that to look. Okay, there we go. So we'll have x is equal to, we'll do the quadratic formula because I don't know how to really, I'm personally terrible at factoring when there's like a something other than 1 out in the front. I remember doing something like that in like, what was it, like algebra 1 we did that, and honestly, it was like just guessing, and I was like, all right, no, I'm done with this. Like, this isn't happening. But I like to do quadratic formula for these. So we get 8, 4, so we'll end up with a negative 1 plus or minus 3 over 4. So we get x is equal to, this will be I believe we'll get a 1/2, right? We have a negative 1 plus 3 is 2 over 4 is 1/2, and we'll also get we'll get negative 4 over 4, we get negative 1. So our two factors here is x minus 1/2 and x plus 1, right? We have to reverse the signs again. So now you may be thinking, okay, well, we didn't get any of these factors to cancel off. Did we possibly make a mistake or something like that? You know, what did we do wrong? Well, we actually didn't do anything wrong, and it's going to be good for us because we'll actually end up getting a vertical asymptote here. We're going to be getting a limit at infinity. If we were to cancel things off, then we would probably end up with something like a removable discontinuity like we did a couple problems ago. Let me show you what I mean. This denominator here, okay, this is just going to become, as x approaches 1 from the negative side, you're going to have something like negative 0.9 or negative 0.09, and it's just going to get smaller and smaller and smaller, right? And sorry, not negatives. I'm thinking about what I'm going to say next, and this is going to become a very, very small negative quantity, okay? And that's going to get multiplied by some positive quantity, okay? So something like, it's going to become like something close to 3, okay? In which case, you're still going to get a very, very small negative quantity. Okay, and that just makes the denominator, or sorry, the whole fraction as a whole, it's going to become infinitely large, but it's going to become infinitely large in the negative direction. Here's why. Because remember, we concluded that the bottom is negative, right? It's a negative times a positive, we get a negative. On the top, we have a 1 minus a half. We can just plug in 1 for this x. Okay, we get a positive quantity there. 1 minus a half is just a 1/2, and 1 plus 1 is 2. So we get a positive quantity here, we have positive. So this limit, as x approaches 1 from the negative side of 2x squared plus x minus 1 over x squared plus x minus 2, is going to become negative infinity. All right? And the limit as x approaches 1 from the positive side, now we can look at that, is going to be the same. It's going to be the same idea, right? Here what we're going to do is, well, the same exact thing. This, instead of being negative now, since we're approaching 1 from the positive side, we're of something like 1.1 or 1.01 or 1.001, right? So we're going to get a very, very small positive quantity here, which is going to make this fraction as a whole infinitely large. We'll get a positive number here, so we get positive overall, and then here we'll have positive, positive, and so we get a positive overall. So we get that the limit as x approaches 1 from the positive side, okay, is going to, of this function, we'll call it f of x, is equal to infinity. Okay, so there you go. We now know that x equals 1 is indeed a vertical asymptote. But we're not done yet, because we have to look at our other one, -2. So we have to look at this thing approaching -2 from the negative side and the positive side. So let's just copy this down, okay, because we're going to examine it in the same exact way. Okay, and well, as we have a -2 from the negative side, what we're going to see is that our denominator, this thing, will become negative, right? But it'll be an infinitely small negative. It gets multiplied by this won't be positive. We have to look at it a little further. This is going to be -2 minus 1, so this will be a negative, and so we get a positive here. On the bottom, on the top rather, we have a -2 minus a half here. That's -5 halves, and so that's a negative quantity. For the x plus 1, we'll also have a negative quantity, and so that gives us a positive. So this limit will actually end up equaling infinity. Now, copying the same thing, we'll talk about it when we're approaching from the positive side, and see if this is still equal to infinity, or if it's equal to negative infinity. We know it's going to be one of the two. So now what we'll have is this -2 from the positive side will make this a positive quantity. This will still be negative. This will still be negative. This will still be negative. So we have a positive on top and a negative on the bottom. So this thing will equal negative infinity. Okay, so we can conclude that since these things are infinite, right, whether it's negative infinity or infinity, we'll also have x equals -2 being a vertical asymptote. And so we can conclude in the end that our vertical asymptotes are x equals -2 and x equals 1, and we have horizontal asymptotes at y equals 2. I believe that's what it was, right? Y equals 2. Nice. So there you go. All right, so next we're going to start talking about the limit definition of a derivative. Now, I'm asking you to use the limit definition of a derivative to calculate f prime of a when f of x is equal to the square root of 1 minus 2x. Okay? And I have the formula for the limit definition of a derivative down below. Now, you know, the thing about the limit definition of a derivative, okay, it does kind of like suck to do. Like, I hate doing it, but you know what, like, you can check your answer with this because you know how to take a derivative of this in general. Like, you know how to use power rule, chain rule, product rule, all that stuff. So you can take a derivative of it and then check your answer. That's something that you couldn't do when you were originally doing these problems, right? Because you didn't know those rules yet. All right, so we can end up checking our answer with that, but I'll skip that for now. We'll just go right into using this limit definition of a derivative. So we're going to try to find f prime of a. This is equal to the limit as h approaches 0 of f of a plus h. So we're going to do, oops, what did I do there? We'll have the square root of 1 minus 2 times a plus h, right? So we're just plugging in a plus h for x. That's what this notation means. I will say to you that I definitely struggled with that part, right? Like, okay, what does this a plus h mean? What do I do, right? Well, it means you plug it in everywhere you see an x, and then with f of a, you plug in a in everywhere you see an x. And for some reason, when I started, with that stuff, I did struggle with that a little bit. So, I just don't want you to do the same. Okay, so we have 1 minus 2. We'll plug in an a here. Okay, and then we're just going to have this over h. All right, so we're going to distribute this out. Okay, and we're going to get square root of 1 minus a 2a minus 2h, and then we'll have minus the square root of 1 minus 2a over h. Now we're kind of stuck, right? Well, what do we do? Remember, when you're dealing with like radicals, okay, in the limit definition of a derivative, you're most likely going to look to multiply by the conjugate, okay, of that radical that you're going to end up with in the numerator. All right, that's generally how you solve those types of problems. Okay, so that's what we're going to do right now. Okay, if we multiply by the conjugate, okay, meaning that the conjugate is just this thing with a plus sign. Okay, it's going to be the opposite sign. So we're going to have, I can even just highlight it like this. Copy it, paste it, make it smaller, and do this. I'm going to cheat here, guys. I'm not sure what else to, yeah, we'll do that, and we'll make it a plus. Okay, and then I will also paste it again here. 1 minus 2a minus 2h minus a1 minus 2a. That's what we're going to get when we multiply by the conjugate. Okay, we get this piece squared, which is just this, and then the middle terms cancel out, so you get this term squared, and it's going to be a negative. Okay, so then you're going to have this over h times that square root of 1 minus 2a minus 2h plus the square root of 1 minus 2a. All right, and well, now you can see that this 1 is going to cancel out with this 1, and this negative 2a cancels out with this positive 2a because this negative's here, right? And we just have a negative 2h left over with this h right here. So we just end up canceling out the h's, okay? And we have a negative 2 at the limit as h approaches 0 of negative 2 over the square root of 1 minus 2a minus 2h plus the square root of 1 minus 2a. Okay, and now we can just evaluate this limit when h is approaching 0, because we can now plug in 0 for h, and well, that won't affect our denominator anymore, making it 0. Okay, so we can say that this is equal to negative 2 over the square root of 1 minus 2a plus the square root of 1 minus 2a. Okay, and we just end up with this equaling negative 2 over 2 times the square root of 1 minus 2a, and this makes it negative 1 over the square root of 1 minus 2a. All right, and there you go. All right, that is your f prime of a, and you can just even put f prime of a here. Okay, so there you go. That's your derivative with the limit definition of a derivative. When you have something like a polynomial that you're taking a derivative of with the limit definition, you kind of just expand it, and it all is really nice. With a radical, you do the conjugate, and there are some other things too. I believe it's like there's like a 1 over, maybe if you have like a 1 over x or something like that, you would have to end up finding common denominators or something like that. Like, there's a lot of different methods and a lot of different things that you could have, but they generally boil down to, the problems that you're going to get generally boil down to around like 2 to 3 methods that you're going to have to use. One of the most popular problems to put on something like a final is a square root problem. So that's why I put it on. Now, for problem number 8, another limit definition problem, we have a piece of redstone is thrown upward with a velocity of 10 meters per second. Its height after t seconds is given by the function x equals 10t minus 2t squared. Use the limit definition of a derivative to find the velocity of the piece of redstone after 1 second. Okay, so I'll just write that down here. We want to find v of 1, right? We want to find when the piece of redstone will hit the ground. Okay, so we want to find t when x equals 0. That's how I'll write that down. Okay, and then we're going to find the final velocity before hitting the ground. Okay, so that v of t, and I'll point to that. So those are the 3 things that we're trying to find. Okay, so we'll start off with that function, x equals 10t minus 2t squared. Okay, and that is a function of time. So I'll write that x is of t. There we go. Okay, so now what we're going to do is just take a derivative with the limit definition of a derivative, right? Pretty much everything that we're talking about here is talking about velocity, right? We're talking about velocity. So what we're going to do, take that derivative and then find all our stuff. Okay, I wanted to give you more of a physics problem here, right? Something that you have to do with physics, because I want to show you actually like applying the limit definition of a derivative. Okay, so I'm just starting off here, plugging in my a plus h's. Okay, then I'm going to start plugging in just a, right? Then I'm going to put this over h. And of course, you can't forget your limit as h approaches 0. I cannot believe I almost forgot that. Yeah, so this is a polynomial, right? So I said we kind of just expand this. We get a 10a plus 10h minus a 2 times. Now, if you don't know what this expansion is by heart, I'd really recommend learning it, okay, and memorizing it, because this is something you're going to have to deal with for the rest of the time that you're doing math, like you pretty much already have, right? So you should remember that when you expand this, it's a squared plus 2ah plus h squared. Okay, so I would just remember that if you haven't already, and then this thing becomes a negative 2a plus a 2a squared. This is over h. Okay, so let's start. Let's actually we'll do one last expansion here, because we have to distribute out that 2. So we'll do a 2a squared plus 2, no. You have a minus 4ah, and then you have a minus 2h squared, and then you have minus 2a plus 2a squared over h. Okay, from here, this may look like a mess, but it's actually not going to end up being one, because 10a's, these cancel off, your 2a squareds cancel off, and then all the terms left have an h in them, so you can just cancel that off one by one. And then you can write what you end up with down below. The limit as h approaches 0 of, we have a 10 minus 4a minus 2h, and that's it. And we can evaluate the limit now and get 10 minus a 4a, right? And since we know how to take this derivative, let's make sure that that's actually what this derivative will be. If we take this with power rule, we do get a 10 minus 4t, and that's exactly what we just found, right? So, and it's really a bummer to have to use the limit definition of a derivative, but it is something they want to make sure you know. So that's v of a. We're going to make this v of t by just plugging in a t everywhere we see an a. Okay, that's something we can do. And now we have that velocity function. So let's see what we were trying to find. The velocity at t equals 1. So the velocity at 1 equals 10 minus 4, which equals 6. And we can even, did I put a units in the question? Yes, I did. So we'll write 6 meters per second. Right? And yeah, cool. So we have that, great. We can now find the next thing, which is, so we want to find when the piece of redstone will hit the ground, and we want to find its final velocity. So its final velocity actually is something that we can find first, and the reason why I'm saying this is because, remember, if you throw something up in the air, right, its like height versus time graph will be parabolic. Okay, if you've taken a physics class, you'll see that, right? It'll be parabolic, and and you can even see that because we have a parabolic function as our position function here, right? So the time where I guess the position that you're at to start off with, right? When you throw that up, it'll have some velocity. It'll have the exact same velocity when it hits the ground as when you threw it. Okay? Assuming that you're throwing it from the same spot, the same height where it's going to hit the ground. Okay? So let me draw that so I can make that more clear. if you throw something from here, okay, it'll have some initial velocity. Well, that will equal the final velocity if it comes back down and hits in the exact same height. Okay, that's the whole point. Okay, so hopefully that didn't seem too confusing. So what I'm going to do is I'm going to say, okay, what was the initial velocity? What was the velocity when the time equals 0? It equals 10 minus 4 times 0. Well, it equals 10 meters per second, right? Now be very careful here, because your final velocity is not 10 meters per second. Okay, I said the initial velocity was equal to the final velocity, but I was more talking about the absolute value of the velocity, kind of just like the speed, right? The speed will be the same, okay? But this is generally how it works, is your initial velocity is equal to your negative final velocity, because it's coming back down, it's going in a different direction. So what we want to do is, we're using this information, we're going to say, okay, well, plugging into this equation, negative 10, when is that going to be equal to 10 minus 4t, right? Well, we subtract that 10 over, okay? We get negative 20 equals negative 4t, and we find out that t equals 5, okay? So we can write down that v of 5 then, 10 minus 4t, and this is kind of a circular argument, but just to kind of put this down, we get v of 5, 10 minus 4 times 5, we get a negative 10 meters per second, right? So I can show, I mean, like, that was kind of redundant to do, but you still see, yeah, we get negative 10 meters per second for our final velocity. That's when t equals 5. Okay, so there you go. You know, we have all of the parts of the question answered. And if you're kind of confused with the whole process in which I did that, because it was kind of messy, and you know, with physics kind of problems, right? There's a lot of different ways you could have solved that problem. There's a lot of different ways you could have looked at it. You could have maybe analyzed the position function a little bit. You could have done stuff there. But I mean, and you didn't have to know that the initial velocity equals the negative final velocity, okay? There's other ways that you could have done that. That's just the way that came naturally to me, okay? So I'm not saying that that's exactly how you have to do it, right? So moving on to number 9, we're going to be talking now about taking derivatives, okay? Now I'm only going to do one problem with taking derivatives with our power rule, chain rule, and all that stuff, because you know, you guys have had those rules kind of really, you've had to do those over and over and over again. I know I did when I was in Calc 1, because we had to do, you know, related rates, exponential growth and decay, all that stuff, and optimization even, and you just have to do derivatives over and over and over and over again. So I assume you're pretty good with those. I just want to test that knowledge, and you know, you can see, do you have to improve on your derivative rules at all? So we have this problem to do that. So definitely try this problem on your own, see if you can do it. We have we want you to find the derivative of j of x equals 3e to the 4x times sine cubed of 2x. All right. So I want to make sure that you can really take derivatives, so I gave you this. All right. So what do we have to do here? Well, we're going to definitely have some product rule, okay, because we have two separate functions that are being multiplied. We have this 3e to the 4x. We can just group that 3 in with the e. And then we have sine cubed of 2x. All right, but we're also going to have to do chain rule for both of those things, because this is not an e to the x, it's an e to the 4x, and this is not a sine of 2x. Even if it was, we'd still have to do chain rule. This is a sine cubed of 2x. We have kind of like a double chain rule here. So I tried to give you kind of like the hardest reasonable derivative I could find. But yeah, so let's start off with j prime of x. Now remember, you know, when you take a derivative with product rule, okay, here's what I'm doing. When you have uv, take a derivative of it, it's uv prime minus, plus v prime u. Okay, so you just follow that. So let's take a derivative of the worst one. We'll do the worst one first. So we'll do the derivative of sine cubed of 2x first. So we'll start off with 3e to the 4x, right? We'll just bring that down, and then we'll have our sine derivative. So how do we take a derivative of this? Well, first off, let's just start off by doing the outermost thing, right? This is the same thing as saying, we can say that this is this whole thing cubed, right? So we can just say that it is 3 times sine of 2x, and we'll square it, right? But we're not done, because we still have to find the derivative of sine of 2x, and well, the derivative of sine of 2x is going to be 2 cosine of 2x, right? So we have to include that as well, 2 cosine of 2x, right? So we took the took the first derivative, right? And then we had to go on and take our derivative of our inside function, right? And I kind of went through and did chain rule again there, because the derivative of sine of 2x, you have to you get cosine of 2x, but it's not a regular x, it's 2x, so you have to put a 2 out front, right? That's the derivative of 2x. So yeah, that's all your pieces there. And then we'll just do the second part, where we have the derivative of 3e to the 4x, and we keep the sine cubed of 2x. So we'll have a 4 that comes down from the e to the 4x, right? And we'll have this times 3 times e to the 4x, and then we'll have that sine cubed of 2x. Okay, so now we're just going to simplify this, and you guys can do this on your own pretty easily. So let's just go here. This is going to be 18 e to the 4x sine squared of 2x cosine of 2x, and this is going to be plus 12 e to the 4x sine cubed of 2x, and there's your derivative. Okay, so that's kind of the nastiest thing that I could find to do for you guys, but I don't think, there's definitely no way that you'd get anything nastier on your calc final. I don't believe it. I mean, I couldn't see that happening. All right, so now we're going to move on to implicit differentiation, question 10. So we're going to solve for dy dx using implicit differentiation, okay? And we have that the tangent inverse of x squared y equals x plus xy squared, okay? So implicit differentiation, if you are having trouble recalling, because that's not really something that we do for too long when you're going through a calculus 1. Basically, implicit differentiation is when you have kind of the y's in the middle of the equation and you have to take derivatives of it and all that stuff, right? So you have to do some chain rule. So it's basically this, right? So we're trying to find dy dx and y's inline the equation. Like, it's not just like y equals something, it's something with x and y's equals something with x and y's, okay? So what we're going to do here is just take a derivative of both sides and then try to solve for dy dx, okay? And let's start off by taking a derivative of the left-hand side. So we'll take a derivative of this, we'll take a derivative of the right-hand side, but we'll focus on the derivative on the left-hand side first, okay? The derivative of tangent inverse of x is just 1 over 1 plus x squared. So since we have an x squared y, it's going to be 1 over a 1 plus x squared y, and that will get squared, okay? And we have to do some chain rule, right? And we're going to be doing chain rule on our product rule, right? So we'll be doing chain rule on this, because this is inside the tangent inverse, but these two things are being multiplied together, and so we'll have to do some product rule, okay? So the derivative of the inside is going to be 2xy, okay, plus, and then we'll have a x squared y prime. Okay, and I'll abbreviate dy dx as just y prime, okay, the derivative of y, because it's just going to be easier to keep track of it that way. All right, so now we're going to have this equal to the derivative of the right-hand side. The derivative of the right-hand side being, well, we have a 1 plus, and then we have another, well, this is not x squared y, it's xy squared, so we're going to do product rule again. So if we take a derivative of just the x and leave the y alone, we get y squared, and if we take a derivative of now the y piece, we get a 2xy, okay, and we get a y prime. Okay, so And just to slow that down, because I don't want to be taking these derivatives too fast, when you take a derivative of y squared, you're going to get 2y, right? And the x just comes down, okay? So that's how we got the 2xy. And then the derivative of y is y prime. So that's the chain rule that you do, okay? So kind of think of y as its own little function. And so whenever you take a derivative of like y squared or y cubed, right, you're going to have 3y squared y prime or 2y y prime, okay, in this case. So moving on with that, what we're going to do now is just look to solve for y prime, and it looks really disgusting right now, right? So what we're going to do is just try to simplify this as much as possible. So I'm going to just drag this numerator, okay, up to the top of the fraction. So we'll have 2xy plus x squared y prime over 1 plus, and then when we square this piece right here, we will get a x to the 4th y squared. This is now equal to still a 1 plus y squared plus 2xy y prime. Okay, so basically what we have to do now is just get common denominators, or we can just it's the same exact thing as multiplying each side by 1 plus x to the 4th y squared. Okay, so multiply by 1 plus x to the 4th y squared. And this will be a kind of gross distribution, but we got to do it. So this is now equal to, we'll multiply this out here. We get a 1 plus x to the 4th y squared. So I just did this piece times this and then this. And I'll do this piece times this and then this. So that's just the order in which I'm doing it. So we have a plus y squared plus x to the 4th y to the 4th. Then we have plus a 2xy y prime plus a 2x to the 5th y cubed y prime. What we have to do is get all the y primes on one side, factor out that y prime, and well, then that's literally it. We divide the rest over, but it's kind of hard looking at this mess and going, okay, I know exactly what to do, right? So what we're going to do is get all the y primes on one side. So I'm going to subtract this thing over, and I'm going to subtract this thing over, and I'm going to subtract this thing over to this side. So what we're going to have is an x squared y prime minus 2xy y prime minus 2x to the 5th y cubed y prime. And that's going to be equal to 1 plus x to the 4th y squared plus y squared plus x to the 4th y to the 4th minus 2xy. Okay, so now, well, all we have to do, right, why we get all the y primes to the one side is because we're going to factor it out. Okay, so we're going to factor out the y prime, and then we get an x squared minus 2xy minus a 2x to the 5th y to the 3rd. Okay, and that's going to be equal to 1x to the 4th y squared plus y squared plus x to the 4th y to the 4th minus 2xy. Okay, now I think why a lot of people get messed up, maybe, like, my guess is when they get to this point, right, where they're not sure, okay, do I factor out the y prime, or they're looking, instead of factoring out the y prime, they're looking to factor out all the other garbage around y prime and somehow get it together. Like, that's at least a flow of thought that I know I've had before, and I think that might be where people are messing up. I'm just trying to really connect with the problem and make sure I can fix it if, that's a point where you're running into when solving this problem. But that's just my guess, so I'm not really a math doctor. But I don't know. I should stop rambling and solve this problem. All right, and then we divide. So we're just going to divide everything off except for the y prime. And then we have our answer. So we have y prime equals 1 plus x to the 4th y squared plus y squared plus x to the 4th y to the 4th minus 2xy. And then this is equal to a x squared minus 2xy minus 2x to the 5th y to the 3rd. And there you go. Okay. So that's really gross, but that is your answer. All right, so let's move on to our next problem. We have number 11 here. We're going to find the derivative of f of x equals the inverse tangent of x via implicit differentiation. Okay? Now, looking at this, you might be like, okay, I have no idea where to go from here, but it's actually not the hardest problem in the world. It's just very unintuitive for somebody that's never looked at something like this before. Okay? Let me show you what I mean. So f of x, we'll rewrite that as y. Okay? And that's equal to the tangent inverse of x. That means that, and the reason why we're doing implicitly here, we're not just going to take a derivative of both sides, right? Because, you know, you just as we did in the last problem, we know the derivative of this by heart. Okay, most of you know the derivative of this by heart, and you should for your Calc 1 exam. But we want to actually derive this. We want to figure out how we actually get the derivative of inverse tangent of x, and we can do that with implicit differentiation. Okay, that's why I wanted to show you this. It's actually kind of cool. So this is the same thing as saying x is the tangent of y, right? That's the whole idea of an inverse tangent. Okay, so now we actually will do implicit differentiation. We'll take a derivative of both sides. Okay, so we'll do d dx, okay, and we get 1 on this side, and we'll get a secant squared y, right? Just the derivative of your tangent, and then we have the, you know, we'll have a chain rule because the derivative of y is y prime. Okay, so now we get that, well, y prime is equal to 1 over secant squared y. Okay, you may be tempted to just say, okay, well, y prime then equals cosine of y, but that, or cosine squared of y, but that doesn't really help us, right? That doesn't get us our 1 over 1 plus x squared. So we got to figure out how to do that. All right, well, here is kind of how we go about that. We're going to use a trig identity here, okay? And this is where it kind of becomes a little unintuitive. And so what we're doing here is we're going to say, okay, well, secant squared, we know, is equal to 1 plus tangent squared. So we're going to say that this is 1 plus tangent squared y. And we're almost done here. The only thing that we have to do next is realize that, well, tangent squared of our tangent of y was equal to x up here before we took derivatives on both sides. So this is literally just the same thing as 1 over 1 plus x squared. And there you have it. Okay? So that's actually how you end up doing that. You know, I don't think that's really a problem that you'll have on your final, but I think it's really good, a really good practice for implicit differentiation. If you can do something like that, I think you are set as far as any implicit differentiation problem that you could possibly have. So moving on to our next section, now that we finished implicit differentiation, guys, we are so close to being done. We're on to our exponential growth and decay section now, question 12. So we have a cup of chocolate milk. I'm very fond of chocolate milk. It is taken from the refrigerator, which had a temp of 5 degrees Celsius, into a room with a temperature of 20 degrees Celsius. It reaches a temperature of 10 degrees Celsius after 25 minutes has elapsed. What is the temperature of the drink after 50 minutes? Okay, so this is a Newton's law of cooling problem, even though we're heating here, so that's kind of weird, right? But I believe that you'll be provided with this equation, though I'm not 100% sure. I don't know, you know, it depends on if you're taking the AP test or if you're taking just a regular Calc 1 exam. You know, maybe you didn't even cover exponential growth and decay. I'm not 100% sure. But if regardless, I will give you the Newton's law of cooling formula here. Okay, so what Newton's law of cooling says is that the change in temperature over time, or over the change in time, right, that equals K, right, time, and that K, it's kind of like your rate, right, times T, right, so the temperature as a function of time, okay, of your object, minus the surrounding temperature, okay. So what we generally do here is we say that, okay, t minus ts is a function of y. Okay, so we call this a function of y, the difference between the temperature of the object, which is chocolate milk in this case, with respect to time, minus the temperature of the surroundings. At time equals 0, we know that the temperature as a function of time is 5 degrees Celsius, and the surrounding temperature is 20. So our initial y is negative 15. Okay? Later, what ends up happening is our y at 25 becomes 10 minus 20, right? So our temperature increases to 10. So we have negative 10 there now. Now the whole reason why we defined this y as we did is because, well, t of s is a constant. So when we take a derivative of this equation here, we get y prime of t is equal to t prime of t, right? If that's true, well, then we know that this equation, okay, also equals dy dt, okay? So what we can do, I'll make this just look a little bit cleaner for now, is we can write dy dt equals ky, right? K, and then this is y. Okay, and all we have to do is just move these things around a little bit. So we can move this to dy over y equals k dt. Okay, and then this part is generally, I believe, kind of glossed over because you haven't really done any integration yet, but you can integrate both sides here, and eventually what you end up getting, so I'll kind of gloss over it too. Actually, no, this is a final review, so you guys have already done integration. So this becomes natural log of y equals kt plus c, and you can take an exponential on both sides, and you get that y equals e to the kt, and we can just write this as times e to the c. Okay, that's a property of exponentials. And then this just becomes, well, e to the c is a constant, and that constant is y naught, or y of 0. So we write this as y of t equals y of 0 e to the kt. Okay? And we know that y of 0 is negative 15. Okay? So, all we have to do now, right? We have to find our k. We need to find our rate, okay? And that's it, right? We have done the hardest part of the problem. And then all we have to do is plug in 50 for our time and see what we get, okay? That's literally it. I mean, the rate, though, is the hardest part of the problem. Setting up everything, getting the rate, and then it's all downhill from there. So let's just find the rate. How we're going to do that is by plugging in our known right here. Okay, y of 25 equals negative 10. So y of 25, so this is negative 10, equals, and I'll drag this down a little bit because this isn't really part of the same. Like, this is our equation, and then we're going to actually do something with it here. So negative 10 equals negative 15 e to the k times, remember we are at 25 minutes after, so I'll put a 25 there. Okay, we divide by negative 15 on both sides, and we get 2/3 is equal to e to the 25k. Taking a natural log of both sides, we get natural log of 2/3 equals 25k. And then we just get k is equal to natural log of 2/3 divided by 25. Okay, we found our rate. So all we have to do now is plug in to an equation, right? We're going to plug in for this equation, okay? But instead of finding what y of t is, right, we're going to find what t of t is, okay? That's the idea, because we want to find what the temperature is going to be after 50 minutes. So we know that t of t is going to be equal to ts plus y of t, right? That's just manipulating the equation that we previously had, okay? Well, we know that our time is 50 minutes, okay? Our surrounding temperature is 20 degrees Celsius, and our y of t equation is now going to be negative 15. So we can actually make this a minus. So minus 15 e to the k, which is natural log of 2/3, over 25, okay, times t, which we know is 50. Okay, so simplifying this, we get 20 minus, this is just a 15, and, well, this, first off, this natural log is going to counteract with that e, and you'll just end up with 2/3 there, but you have to also deal with this 50 over 25, which is 2, which will basically put a 2 out in front of that natural log, and so what you're going to end up getting is a 2/3 squared. Okay, so knowing that, what we're going to do is we'll get 20 times 15, or 20 minus 15 times 4 over 9. Okay, and so we get t of 50 is equal to 20 minus 60 over 9, which is equal to, we can get common denominators here, 180 minus 60 over 90, or sorry, not 90, 9, and we get 120 over 9. Okay, now I'm not going to ask you to compute that or anything like that, but that ends up being, I believe, 13.3 repeating degrees Celsius. Okay, so, Newton's law of cooling is kind of hard to understand because it's like, it's an actual application, and, I always, personally for me, I always had trouble with kind of like exponential decay, growth, and all that stuff because there were so many different equations to use, and I just wasn't sure. But with Newton's law of cooling, you have a set equation. You need to figure out what to do with it. So if you have done Newton's law of cooling in your Calculus 1 class, which if you're watching at this point, I assume you have, definitely make sure that you go over these equations or find out if they're going to be given to you, and then go from there. And that's going to help you prepare for your final. So now let's move on to related rates. Now, we're going to start off with an easier problem here, okay, so we can kind of ease our way into related rates, okay. Now, related rates is no optimization, okay, but it's not very pleasant either for most students because it's a very common problem, especially on the AP test. I believe if you guys are in AP, by the way, and you're doing some past AP tests and one comes up about like a potato or something like that, yeah, that was my AP test, and it was terrible, and I hated it. That was an awful problem. I can't believe I did. I don't know how I did well on that problem. A cylindrical fish tank with a radius of 5 meters is filling with water at a rate of 3 meters cubed per minute. How quick is the height increasing? Okay, so all we're trying to find here is dH/dt. Okay, we're trying to find dH/dt. Now, what do we know about cylinders? Okay, like that's kind of what you have to think about when you talk about related rates. Okay, we're dealing with a cylinder here. Okay, it's a cylinder that's filling. So if it's filling, okay, we're talking about meters cubed and all that stuff. We're talking about volume. So we need to have the equation for the volume of the cylinder, and that's pretty easy, right? And you don't have to remember that because all you have to remember is the area of a circle, which is pi r squared. That's the base of your cylinder. Okay, you multiply that by how far it extrudes into the third dimension, which is your height. Right? So pi r squared's down here, height's there. That's your cylinder equation. Okay? So it's not the worst thing in the world. And it's not something you actually have to remember. You can just kind of figure it out yourself. Okay? All we have to do here, because we have our equation for our volume, but we might not know what to do with it. You might not know what to do with it, and generally the answer is always take a derivative when you're in Calc 1. But I'll kind of make that a little more. I'll make a little more sense when I'll actually have you understand it when I'm trying to explain it right now. But we need to figure out what our givens actually are telling us, and that is going to really, really help understand why we're taking a derivative here. Okay, 3 meters cubed per minute. That is the rate that the volume is changing. Okay, 3 meters cubed per minute is the rate that the volume is changing, and so all we have to do now, like I just said, is take a derivative. Okay, we take a derivative of each side, And you need to realize before you take a derivative that pi r squared is a constant and h is a function of time, right? Because height is increasing, so it's changing with time. So this, you can kind of rewrite this as v of t equals pi r squared times h of t. That's how I would rewrite it. Now, you can take a derivative with respect to time on both sides. Okay, and you get v prime of t, which is dv dt. So actually, I'll rewrite it like that. dv dt is equal to pi r squared times dh dt. And remember, dh dt is what we're trying to find. So we do dv dt divided by pi r squared, and that's equal to dh dt. And we know all of this stuff, right? So making this look just a little bit nicer, we'll do that. And this is equal to 3 meters cubed per minute divided by pi times r squared, which is 5 meters, and that gets squared. Okay? And now, I'm not sure if y'all are any physics students or physics majors or anything like that, but you will need to check your units, all throughout physics. So really make sure, and probably some chemistry too. I don't really know too much about the chemistry field, but make sure that you are checking your units for this problem to make sure that it comes out okay, right? You get a 3 meters cubed per minute, and you divide that by pi times, not 5. This will be a 25 meters squared. Okay, meters squared cancels out with meters cubed, and gives you just a meters on top. So really, this is just dh dt equals 3 over 25 pi meters per minute. And there you go. You have your answer. Okay, so all we really did was, we figured out what was the best equation to use, and, we're talking about something filling. It's giving us a rate that's with meters cubed, so we picked the volume equation for a cylinder. We took a derivative of it because we already know what dv dt is, and we know what the radius is. So the only thing we didn't know was what we were trying to find, dh dt, right? The how quick the height was increasing with time. Okay, so that's the basics of how we did this problem. All right, so moving on to our next related rates problem, which is going to be a little more difficult. It starts off with some random dude. I never named these people. I should have. Should I feel bad? I don't know. All right. Some random dude is sprinting north at 4 feet per second from a starting point P. After 5 minutes, another rando starts walking south at 5 feet per second from a point 500 feet east of point P. At what rate are these randoms moving apart after 20 minutes of the first dude? I did not word that right at all. After the first dude begins sprinting. All right, cool. Wow, great job. All right, so let's draw a diagram because I gave you a lot of information, and what you're gonna have to be able to do is just organize this, right? If you organize this information, then you can draw a graph and figure out what you're actually going to be using as your equation here. Now, we'll start with point P. Okay. And starting from point P, we know that the first dude, begins walking at 5 feet per second north. Okay? So he's walking at 5 feet per second north, and I should make that line a little more straight. Upwards. There we go. Okay. So 5 feet per second. Okay? Now, another person. Okay, let's call this point Q. Doesn't really matter, but another person is going to start walking. I apologize. This person's walking at 4 feet per second. My bad. All right, so this person's walking 4 feet per second because this person is sitting here walking 5 feet per second. Okay, and yeah, I said sprinting. 4 feet per second is not sprinting. I noticed that while I was writing the problem, and I thought that was really funny. So these guys are separated by a distance of 500 feet. Okay, and now you have to be like, okay, well, what equation are we going to use to describe this? I mean, you have kind of this this kind of stair looking thing, right? You have, something going up, across, and up, and it may just seem like really odd, okay? But here's what we have to do, okay? We are essentially using Pythagorean's theorem, okay? And the reason why we're using Pythagorean's theorem is because the change that we're trying to find is the change of this green line right here, okay? And I'm going to call this A prime, okay? I'm going to call that change A prime because this line itself is A. I'm going to call this purple line, which I'll extend up this way. This is going to be B. And then I'm going to extend what other color hasn't I used? Yellow. I'll extend a yellow line over, and that'll be C. Okay? Now C is not changing. B is changing from the first guy walking in the opposite direction of the other dude. Okay? So they're walking in two separate directions. So B is changing. C is not changing. So A's change is going to be solely based on C or on B actually changing and C staying constant. Okay? And actually, before I even go back into the problem, just a quick note: whenever you have something like due north or due east in a problem, or you're talking about just different directions in a problem, you're most likely going to be doing Pythagorean theorem and related rates. Okay, so that's probably something that you'll see. It's a very popular type of related rate question to ask on a final. So that's why I think it's really great to ask this question. But we'll start off with the fact that a squared plus b squared, a squared equals b squared plus c squared. Just realizing now that I kind of did that a little backwards, but whatever. These are all going to be functions of time, okay? Because they have all the potential to change with time. I know not all of them are, but we're just going to represent them like that. Okay? Because all of these guys could change with time. Okay? Now, if you do that, well, what you do, you can take a derivative of both sides because we have to incorporate the actual rates that these sides are changing. So we get 2a, right? That's the derivative there, and then the derivative of a, because it's a function of t, is going to be a prime. Okay? And we just get the same thing going down. So we'll get 2b prime plus 2c prime. Okay? So, it may make more sense to put it like this. A squared, it's like taking the derivative of y squared if you're confused on that. The derivative of y squared is 2y prime. Okay? This is the exact same thing, just showing up 3 separate times. All right? So all we have to do is solve for a prime, so we'll divide each side by 2a, right? And we end up getting that a prime equals, and the 2's go away, bb prime plus cc prime over a, okay? And, well, all we'll have to do now is find, we don't know any of these things except for, we'll have to find A, we'll have to find what B is, we'll have to find we know what B prime is, we know that C isn't changing, and we'll have to find, we don't need to find C, well, we know C is 500, so, okay. Let's start off with stating that B prime, okay, the rate that B is changing at is 4 plus 5. Right, it's 4 feet per second plus 5 feet per second, and that gives you 9 feet per second. Okay, so that's why I said we already know what B prime is. Okay, now we got to find A, B, and C, and here comes not a trickier part, but kind of like a more like a longer part, I guess. We have one guy walking at 4 feet per second for 20 minutes, right? So he's walking at 4 feet per second for 20 minutes. Okay. So 4 feet per second times 60 seconds per minute, or make sure you always do unit conversions. Okay, that's equal to 240 feet per minute. And then we're going to multiply that by how long he's walking for, which is 20 minutes. And you get 4,800 feet. Okay, now we got to talk about the other guy. So that other person's walking at 5 feet per second. And there's 60 seconds per minute. But the problem is that, and once you multiply this out, you'll get 300 feet per minute. But once you multiply this out, you don't get, you're not going to multiply it by 20. You're going to multiply it by 15, because the second person starts walking that's not where I was looking at. Where is it? 5 minutes. Here we go. 5 minutes. So I was looking for some kind of 5, right? 5 minutes after. So they're only walking for 15 minutes. I think that's, honestly, I think the only reason, and I put it in the problem because, honestly, I think that it has the potential to trip a lot of people up, and that's exactly something that people will do on your final. So just watch out for that, okay? Highlight it or something if you see something like that pop up in a problem. But all we're going to do now is add these two things up, add these two distances up, and that's going to be b. Okay? That's the distance away in the vertical direction, and just like the y component. Okay? We know that c is 500 feet. That's given in the problem. We're going to use these things to find what a is. Okay? We get that a is the square root of 9,300 feet squared plus c squared, which is 500 feet squared. And you can use your calculator for this if, this would be a calculator part if it was on your final. Okay? And you'll get 9,300 squared plus 500 squared. You take the square root of that. You get 9313.431162 feet. Okay? So, and I'm only doing all the decimal places just because, when I'm taking a final, I like to do just as many decimal places as possible, so I'm not off by, any, fraction or anything like that, so I, make sure that I don't get a silly point off or something like that. I don't know. It's just something that comforts me to do during a final, so, you don't have to. So, a prime equals b prime plus c prime over a. We know this, right? I just wrote this down up here. Okay. And we'll just plug in now since we have everything. We have 9,300 feet is b, right? Times b prime. B prime we know is 9 feet per second. That's the rate at which b is changing. C doesn't matter because, while c is 500 feet, c is not changed. C is not changing, so this is 0 feet per second. So that component, that whole term just kind of goes away. And a, we know now, is 9313.431162 feet. Okay? And all we have to do now is put this in our calculators, and when you do, you get about 8.99 feet per second, which is very close to 9. And that would make sense because c is not changing. The only thing that's changing is your y component, right? Your b in this case, and those things are so far away at this point that really, the rate at which they are changing is literally the rate at which the hypotenuse is changing. So kind of interesting to see that happen. But yeah, that's your answer. Now, really, when you approach related rates problem, I'll kind of go over this again. You draw a diagram. That's the biggest advice that I can give you guys, because if you draw a diagram, you'll have a better idea of what's going on. And especially you start seeing things at right angles and all that, automatically it's Pythagorean theorem. Whenever you have people traveling in paths, even, it's most likely going to be Pythagorean theorem, unless they are traveling in a circle or just, I don't know, something like that. But you kind of understand the idea of what's going on here, okay? Anytime they ask you something like that, it's most likely going to be a Pythagorean theorem question. It's very popular for a final, but something also that's popular is those volume questions, the one we did before. So, those are kind of the questions that you'll probably see on a final. All right, so moving on to our second to last problem on linear approximations. Now we're being asked to find the linearization of the function f of x equals the square root of x plus 3 at a equals 1 and estimate what square root of 3.98 is. Now let me tell you something about linearization, okay? I don't know if this thing is actually ever useful. I don't know if maybe calculators use it or something like that. I haven't done enough research on it. But honestly, I hate this. I hate that we have to learn this because like I've never used it ever in like any of my other calculus classes or ordinary differential equations, linear algebra. It's never came up ever again. So what I would say is just remember the formula and go with it, okay? But I think the main purpose of it, at least, is to make square roots nicer, like or you know, other things like that. They make them nicer. Maybe that might be how calculators actually do it. So like the square root of 3.98 is something we have to find. A calculator might use a linearization formula and convert something gross like that into like a fraction, and then just do that division and then give you a number. That's what I'm assuming is going on here. We got to find the linearization of this function. So the first thing we're going to start off by doing, we need to find a couple things. We need to find f of a. We need to find f prime of a. Now a is 1, so we need to find f of 1. Okay, so we need to plug in 1 to x plus 3, right? Which is the square root of 1 plus 3, which is 2. Okay, so we just plug in 1 to this and we get f of a. Now we have to take a derivative of this, okay, to get f prime of a. And just so we're taking a derivative, I'll call this x for now, right? Because I don't, you know, a is a plugged in number, so we can't really take a derivative of that. We have to take a derivative with respect to x. Don't want to confuse you with that because we're almost done, but if you take a derivative of the square root of x plus 3, I'll actually do it for you and not just tell you the memorized derivative. X plus 3 to the 1/2, okay, is going to be 1/2. The derivative of the inside is 1, so you don't need to worry about that. But 1/2 x plus 3 to the negative 1/2, which is just going to be 1 over 2 rad x plus 3. Okay, when you plug in 1, you get 1 over 2 rad 4, which is just going to be 1 over 4. Okay, so now you have your f prime of a, you have your f of a, and you can plug into your linear approximation formula. So L of x equals f of a is 2 plus f prime of a is 1/4, and you have an x minus a. A we know is 1, so we can put that right in there. Okay, so now what's left to do, we're going to just distribute that 1/4. We get x over 4 minus a 1/4. We can combine the 2 and the 1/4 to get a 7/4 plus x over 4. Okay, and that is the linearization. But we're going to now use this to approximate what the square root of 3.98 is. Okay, now all you have to do this is just find out what the x is here. Okay, well, our function is the square root of x plus 3. To get to 3.98, x has to be 0.98. So we're just going to plug that in and call it good. Okay, so we get 7 over 4 plus 0.98 over 4. All right, so plugging that into your calculator, you're going to get 1.995. All right, and that is it. Okay, so yeah, it's kind of tedious. I mean, but it's not really it's definitely not the hardest problem that you're going to have on your final, not even close. So it's kind of just like a little bit of a break in a way. Just make sure it's not something that you forget. So it's kind of the first time that you're seeing it. So, you know, that's why I guess I'm glad that we're going over this problem now. All right, so for our last problem, we are going to be talking about differentials. Now, differentials do pop up again in Calculus 3 because you talk about differentials in multiple dimensions. So, you know, you are going to be dealing with them again, but they're still a pretty simple idea compared to some of the other stuff that you have to do in Calc 1. Okay, so we're going to be finding dy when y equals the square root of 3 plus x squared, x equals 1, and dx equals negative 0.1. Now, for differentials, I mean, really what it comes down to is that you have dy. Instead of having dy over dx is equal to, you know, whatever your derivative is with respect to x, what ends up happening is you just multiply the dx over and you get dy equals f prime of x times dx. Okay, so basically what a differential tells you is if you move over by a certain amount x, how far up are you going to move y? So it's essentially telling you, you know, it's essentially telling you your slope, right? But it's as a kind of like as a function of how far you're moving over on x, which, you know, kind of interesting stuff, I guess. More interesting than linear approximations. But basically what we're going to do here now is just take a derivative of our equation, right? So we have dy dx equals, well, we'll have we can rewrite this thing as 3 plus x squared to the 1/2. So taking a derivative of that, we'd get 1/2 times 3 plus x squared to the negative 1/2. And we'll get times the derivative of the derivative of the inside being 2x. Okay, so putting that all together to make it look a little bit nicer, we're going to get x over the square root of 3 plus x squared. Okay, because this 2 will cancel out with this 2. So that's not bad, right? We just multiply that dx over, and we get that dy, right, our differential, is equal to x dx over the square root of 3 plus x squared. Now all that's left to do is plug in our x and plug in our dx, and then we're done. Okay, so we plug in 1 for x, and we plug in negative 0.1 for dx. Okay, and we plug in 1 again for our square root. So we end up getting negative 0.1 over, that'll be over 2, right? So dy will end up being, if it's a negative 0.1 over 2, that'll just be a negative 0.05. Okay? So that is your final answer for what your differential actually is. Okay? So that's it for our part 1 of our Calculus 1 final review. I really hope you guys enjoyed it. I hope it helped you, and I hope that your final will go much better now that you've watched this video. But also, we have a part 2 coming up. I'll release that in a couple days if you're somehow taking your Calc 1 final like in the next week or two. I'll be doing, I have written on the board over here, I'll be doing mins and maxes, I'll be doing mean value theorem, I'll be doing showing how derivatives affect like the shape of a graph, we'll be doing L'Hopital's rule, optimization, and we'll be doing all the integral stuff that you learned all up to u substitution. That's where kind of Calc 1 generally stops, okay, and Calc 2 begins. Okay, so again, I really hope you guys enjoyed, and subscribe for some more content, because you know you might be needing me later down the road, and I'm also just I'm a cool guy, I guess. But anyways, yeah, I'll see you soon, and yeah.